Hello, and welcome to Quiet Learning for Sleep. This is your peaceful space to unwind, to let go of the day, and to drift into deep, restful sleep while learning softly about our universe. Here, we take gentle journeys through calm ideas, stories from science and nature, space and time, history and life, all whispered at a soft pace, without rush, without noise, and without pressure. You do not need to focus or remember anything. This is learning the quiet way, where your mind floats and drifts and rests, while curiosity stays softly awake in the background. If you'd like, before you get comfortable, you can subscribe and gently like this video. Doing it now means you won't forget later, and it helps others like you find this calm, sleepy corner of the world. Now, allow your breath to slow just a little. Let your shoulders relax. Let your thoughts soften, like clouds drifting across a calm evening sky. There is nowhere you need to go, nothing you need to do, and nothing expected from you here. This time belongs to rest, comfort, and gentle curiosity. And if you drift to sleep along the way, that is not only allowed, it is welcome. So settle in, let yourself melt into stillness, and allow your mind to float quietly as we begin. In the late 1960s and early 1970s, a quiet realization spread among astronomers and engineers working on long-term planetary exploration. The outer planets of the solar system were slowly moving into a rare geometric arrangement, one that would allow a spacecraft launched from Earth to visit multiple giant planets in a single journey. This alignment was not perfect, but it was close enough to make something extraordinary possible. A mission that could travel from Jupiter to Saturn, then onward toward Uranus and Neptune, using the gravity of each planet to shape and accelerate its path. Such an opportunity appears roughly once every 175 years. Missing it would mean waiting longer than a human lifetime for another chance. This technique, known as gravitational assist or gravity slingshot, was well understood mathematically, but had never been used on such an ambitious scale. By carefully flying past a planet, a spacecraft could exchange momentum with it, gaining speed and altering its trajectory without expending fuel. In practical terms, this meant a spacecraft could reach the outer solar system far faster and far more efficiently than any chemical rocket alone would allow. Voyager was not just a mission to visit planets. It was a demonstration of using the solar system itself as part of the propulsion system. At the center of this planning effort was NASA's Jet Propulsion Laboratory, where mission designers began outlining what was initially called the Grand Tour. The original concept involved multiple spacecraft visiting all 4 giant planets, and possibly beyond. Budget constraints eventually scaled the plan down, but the core idea survived. Instead of a single complex mission, 2 robust spacecraft would be built, each capable of independent exploration and long-term operation far from Earth. These would become Voyager One and Voyager 2. The political and cultural environment of the time also shaped the mission. The Apollo program had demonstrated that humanity could leave Earth, but it was enormously expensive and focused on short-term achievement. Voyager represented a different philosophy, slower, quieter, and oriented toward knowledge rather than spectacle. It was approved during the Cold War, yet it carried no military purpose and no strategic urgency. Its value lay in observation, measurement, and patience. Voyager was designed to ask questions, not to prove dominance. Technically, Voyager had to be unlike any spacecraft built before it. It needed to operate autonomously for long periods, adjusting its orientation, managing power, and protecting itself from radiation without constant human intervention. Communication delays would grow from minutes to hours as distance increased, making real-time control impossible. Voyager's onboard computers, modest by modern standards, were revolutionary for their time, capable of executing stored commands and responding to changing conditions in deep space. Power was another defining challenge. Solar panels become ineffective beyond the orbit of Jupiter, so Voyager relied on radioisotope thermoelectric generators, or RTGs, which convert heat from the natural decay of plutonium-238 into electricity. This choice was deliberate and conservative. RTGS produce small but steady power over decades, allowing Voyager to continue operating long after its primary mission objectives were complete. From the beginning, engineers understood that Voyager might function far longer than originally planned, quietly continuing its journey as long as power allowed. The scientific goals of Voyager were broad and fundamental. At Jupiter and Saturn, it would study atmospheres, magnetic fields, radiation environments, and moons. It would measure charged particles, cosmic rays, and interplanetary plasma. It would observe ring systems in detail and search for geological activity on distant moons. Every instrument on board was chosen to answer basic questions about how planetary systems form and evolve. Yet Voyager was also built with humility. Its designers did not assume success. The spacecraft would pass through intense radiation near Jupiter, a region capable of damaging electronics and overwhelming instruments. It would fly close to Saturn's rings, where even small particles could pose a risk at high speed. Beyond Saturn, conditions were largely unknown. The mission accepted risk as a necessary part of exploration, but it mitigated that risk through redundancy, careful engineering, and conservative decision-making. One of the most remarkable aspects of Voyager's design was its openness to an undefined future. While its primary mission focused on planetary encounters lasting a few years, its trajectory pointed outward, away from the Sun. If it survived, Voyager would naturally continue into interstellar space. This possibility was not treated as an afterthought, but as a legitimate extension of the mission. Voyager was, in effect, a bridge between planetary science and interstellar exploration. The decision to launch 2 spacecraft, rather than 1, was both practical and philosophical. Redundancy increased the likelihood that at least one would succeed. At the same time, differing trajectories allowed mission planners to prioritize different scientific outcomes. Voyager 2 would attempt the full grand tour, while Voyager 1 would focus on Jupiter and Saturn, with a trajectory optimized for close study of Saturn's moon Titan. These choices would later define the very different paths the 2 spacecraft would take. Voyager was approved not because its outcome was guaranteed, but because the opportunity was unique and fleeting. It was launched at a moment when technology, planetary motion, and human curiosity aligned. It represented a commitment to long-term thinking, to sending a machine farther than any before it, knowing that its most distant discoveries might come decades after launch, long after the people who built it had moved on. In this way, Voyager was never just a spacecraft. It was a statement about how humanity chooses to explore, slowly, carefully, with attention to detail, and with the acceptance that some journeys are worth beginning even when their end cannot be fully known. Voyager was launched not to reach a destination, but to begin a process of moving steadily outward, carrying instruments, measurements, and eventually a quiet message about where it came from. The journey itself was the purpose, and once begun, it would not turn back. Long before Voyager One left Earth, its designers faced a question that had nothing to do with propulsion, navigation, or electronics. It was a question about time, distance, and intention. Voyager would travel farther than any spacecraft before it, and if it survived long enough, it would eventually move beyond the influence of the sun entirely, drifting through interstellar space for millions, perhaps billions of years. In that vast future, Voyager would no longer be a mission. It would become an artifact. The question was whether it should carry something more than instruments and antennas, whether it should carry a trace of the civilization that sent it. The idea of placing a message aboard Voyager was proposed by a small group of scientists, led by Carl Sagan. This was not a communication system in any practical sense. There was no expectation that the message would ever be received, decoded, or understood. Instead, it was conceived as a symbolic gesture, a way of acknowledging that Voyager might outlast Earth itself. The message would not be aimed at a specific recipient. It would be addressed to time itself. What emerged from this idea was the Golden Record, a gold-plated copper phonograph disc mounted to the side of Voyager One. It was not decorative. It was engineered to survive extreme cold, radiation, and time. Gold was chosen because it resists corrosion and degradation. The record was encased in a protective aluminum cover, which also carried etched instructions explaining how to play it, using symbols grounded in fundamental physics rather than human language. These instructions were designed to be interpretable by any scientifically literate intelligence, regardless of origin. The record itself contains sounds and images intended to represent Earth and humanity in the broadest possible sense. It begins with a series of greetings, spoken in 55 human languages, ranging from ancient to modern, common to rare. These greetings are not political statements. They do not name nations or leaders. They simply say hello. Some are formal, some are warm, some are playful. Together, they create a sense of diversity without hierarchy. Following the greetings are natural sounds of Earth: wind, rain, thunder, waves breaking on shore. There are sounds of animals, birds, insects, whales. There are human sounds as well: footsteps, laughter, a heartbeat, a mother speaking to her child. These recordings were chosen carefully to convey the idea of life without explanation. They do not describe Earth. They demonstrate it. Music occupies a significant portion of the Golden Record. It includes selections from many cultures and eras, from ancient chants to classical compositions to modern pieces. Bach appears alongside traditional music from Africa, Asia, and the Americas. The intention was not to define the best of human music, but to show variation, structure, and emotion. Music, after all, is one of the few forms of expression that does not rely on translation to convey meaning. The visual portion of the record consists of 115 encoded images. These images are not photographs in the conventional sense. They are analog data encoded as audio waveforms, meant to be reconstructed by a receiver who understands the playback instructions. The images depict mathematics, physics, chemistry, DNA structure, human anatomy, landscapes, animals, cities, and everyday activities. They show humans eating, working, learning, and interacting. Importantly, they also show Earth from space, a small, fragile world suspended in darkness. Technical information is included as well. One image shows the location of Earth, using pulsars as reference points, each marked by its unique frequency. Pulsars are highly stable, making them natural cosmic clocks. This map allows Earth's position to be triangulated relative to the galaxy, at least for a limited period in cosmic time. Another diagram explains the basic units of time and distance using the hydrogen atom, a universal reference likely to be understood by any advanced scientific civilization. Nothing on the Golden Record claims permanence or importance. There is no declaration of dominance, no explanation of technology, no instruction manual for human civilization. The message is intentionally modest. It assumes nothing about the recipient. It offers information, not guidance. From a mission planning perspective, the Golden Record had no scientific value. It did not assist Voyager One in navigating space. It did not help collect data. It did not improve communication. Yet it was approved and included because Voyager was already leaving the solar system. The additional mass was negligible. The symbolic value was immense. Once Voyager One launched, the Golden Record became unreachable. There is no mechanism to retrieve it, no plan to update it, no way to know whether it will ever be encountered. It now travels outward at roughly 17 kilometers per second, moving away from Earth along with the spacecraft itself. Every year, it becomes more distant, more isolated, and more permanent. The record is not meant to be listened to by us again. Its audience is hypothetical. Its value lies in the act of sending it, not in the likelihood of reception. It represents a moment when a technological civilization chose to acknowledge its existence without expectation of response. In this sense, the Golden Record is not a message from humanity. It is a message about humanity, about curiosity, restraint, diversity, and the willingness to think beyond immediate returns. Voyager One carries it silently, without broadcast, without announcement, letting time decide whether it remains unread forever or becomes, someday, a discovered relic. As Voyager continues outward, the record remains fixed to its side, enduring radiation, vacuum, and cold. Long after Voyager's instruments fall silent, long after its power fades, the Golden Record will remain intact, moving through interstellar space as a quiet archive of a single moment in Earth's history. It does not promise that we survived. It does not explain who we became. It simply says that once, a species looked outward, built a machine, and chose to leave a trace of itself behind, not in hope, not in fear, but in curiosity. Voyager One's journey began with a detail that often surprises people hearing the story for the first time. It was not the first Voyager to leave Earth. Voyager 2 launched earlier, on August 20th, 1977, while Voyager 1 followed 16 days later, on September 5th. This ordering was not accidental, and not a mistake in naming. It was the result of careful mission design, shaped by the geometry of the solar system and the different roles each spacecraft was meant to play. The numbers did not reflect launch order. They reflected priority of arrival and scientific focus. The two spacecraft were built to be nearly identical, but their paths through space were planned to be different. Voyager 2 was assigned the longer, more flexible trajectory, one that preserved the possibility of continuing beyond Saturn to Uranus and Neptune. That path required an earlier launch window and greater tolerance for timing uncertainties. Voyager 1, on the other hand, was given a shorter, faster route, designed to reach Jupiter and Saturn sooner, with a trajectory optimized for close scientific study rather than long-term flexibility. Because of this difference, Voyager 1 could launch later and still arrive at its destinations first. This distinction highlights an important principle of deep space travel. Speed is not determined primarily by how powerful the rocket is at launch, but by how efficiently a spacecraft is placed onto the right solar orbit. Voyager 1's trajectory dipped slightly inward toward the Sun before arcing outward toward Jupiter. This inward fall allowed the spacecraft to convert gravitational energy into velocity, increasing its speed without burning additional fuel. In spaceflight, gravity is not an obstacle to overcome, but a tool to be used. Voyager 1 was launched aboard the Titan IIIe Centaur launch vehicle, one of the most capable deep space rockets of its era. The Titan stages provided the initial lift from Earth, pushing the spacecraft beyond the atmosphere and most of Earth's gravity. The Centaur upper stage then performed the most critical task, a precisely timed burn that sent Voyager 1 onto its interplanetary trajectory. This burn was not about brute force. It was about accuracy. A small error in timing or duration would have caused Voyager 1 to miss Jupiter entirely, not by kilometers, but by millions of kilometers. During launch, that precision was tested. A partial shutdown in one of the earlier rocket stages forced the Centaur to compensate by burning longer than planned. For a brief moment, the entire mission balanced on seconds of fuel and small adjustments made automatically by onboard guidance systems. There was no dramatic explosion, no visible crisis, just a quiet correction carried out by computers, doing exactly what it had been designed to do. Voyager 1 achieved the necessary escape trajectory with very little margin, and the mission moved forward. Once separated from its final rocket stage, Voyager 1 entered a phase that would become familiar over the decades to come. Long periods of quiet motion, punctuated by careful checks and small adjustments. It was now in solar orbit, no longer bound to Earth, but not yet interacting with any planet. Its speed relative to the Sun was already extraordinary by human standards, tens of thousands of kilometers per hour. Yet, there was no sensation of movement. Space provides no reference points, no wind, no vibration. Voyager 1 simply coasted, rotating slowly to maintain thermal balance, while its high-gain antenna remained carefully aligned toward Earth. In the months following launch, engineers focused on confirming that Voyager One could survive the long journey ahead. Instruments were powered on gradually and tested one at a time. Some were shut down again to conserve energy, while others remained active to monitor the space environment. The spacecraft's attitude control system used small thrusters to maintain orientation, guided by gyroscopes and star sensors. Communication delays were already growing, measured in minutes rather than seconds, reinforcing the need for autonomy. Commands were planned days or weeks in advance, transmitted as sequences for Voyager One to execute on its own. As Voyager One traveled outward, its speed relative to Earth changed constantly due to Earth's own motion around the Sun. But relative to the Sun itself, the frame of reference that matters for deep space exploration, Voyager One was steadily accelerating along its planned path. By the time it was well on its way to Jupiter, its heliocentric speed was approaching what would become its long-term cruising velocity through the outer solar system. This acceleration did not come from engines firing, but from careful placement on a trajectory shaped by gravity. The decision to send Voyager One on this faster route was closely tied to the mission's scientific priorities. Saturn's moon Titan was a key target, known even then to possess a thick atmosphere unlike any other moon in the solar system. Studying Titan required a close flyby at a specific angle, one that would permanently alter Voyager One's path and prevent it from continuing on to Uranus and Neptune. Mission planners accepted this trade-off. Voyager One would sacrifice future planetary encounters in exchange for detailed data from Titan and Saturn. This choice also explains why Voyager 2 needed to launch first. Its trajectory had to remain adaptable after Saturn, preserving the option to continue the so-called Grand Tour. Voyager 1's path, by contrast, was intentionally decisive. Once it passed Saturn, there would be no turning back, no second chance at additional planets. The two spacecraft were not rivals. They were complementary explorers, each designed to answer different questions using the same rare planetary alignment. As Voyager 1 approached Jupiter, navigation became increasingly precise. Small trajectory correction maneuvers ensured that the spacecraft would pass behind the planet at exactly the right distance and orientation to receive a gravitational assist. This flyby would not only provide close-up observations of Jupiter and its moons, but would also increase Voyager 1's outward speed and bend its path towards Saturn. From this point onward, gravity would become the dominant force shaping the mission's future. Even before that first planetary encounter, Voyager 1's fate was becoming clear. Its speed relative to the Sun was already sufficient to escape the solar system entirely. Provided nothing intervened to slow it down, Voyager 1 was on a one-way path outward, destined to leave the planetary region behind and continue into interstellar space. At the time, this was acknowledged, but not emphasized. Voyager 1 was still considered a planetary probe, its distance measured in astronomical units, its communication delay still short enough to feel manageable. Yet the foundations of its later journey were already in place. The launch sequence, the choice of trajectory, the early accumulation of speed, all of these decisions quietly committed Voyager 1 to a future far beyond its original mission goals. it was not launched to leave the solar system, but it was launched in a way that made leaving inevitable. Voyager One's launch was brief, lasting only minutes, but its consequences stretch across decades and light years. It launched second because it could afford to. It traveled faster because its mission demanded it. And from the moment it separated from its final rocket stage, it began a journey defined not by thrust, but by gravity, precision, and time. The engines fell silent, the spacecraft coasted on, and the long outward story of Voyager One truly began. After launch, Voyager One entered a phase of the mission that is often overlooked because it lacks dramatic encounters, yet it is one of the most important parts of the entire journey. This was the long passage through the inner solar system, a period defined not by sudden discoveries, but by distance steadily accumulating. During this time, Voyager One was no longer an Earth mission, and not yet a planetary visitor. It was a deep space traveler in transition, moving outward through regions where the sun still dominated gravity, light, and energy, but where Earth was already beginning to feel far away. In the months following launch, Voyager One's motion was governed almost entirely by the orbit it had been placed on by its launch vehicle. No major engine burns lay ahead. Instead, the spacecraft coasted along a carefully calculated path around the sun, gradually increasing its distance while maintaining a stable orientation. Its speed relative to the sun was already immense by human standards, measured in tens of thousands of kilometers per hour, yet that speed felt meaningless without reference points. Space offers no sense of acceleration. Voyager One simply existed in motion, its velocity locked in by physics rather than propulsion. During this period, mission controllers focused on verification rather than exploration. Every system on board had to prove that it could survive years, not days. The spacecraft's 3 onboard computers managed command execution, attitude control, and data handling, each designed with redundancy to tolerate failures. Voyager One slowly rotated to distribute heat evenly across its structure, a process known as thermal balancing. Without an atmosphere to carry heat away, temperature control depended entirely on orientation, insulation, and careful power management. Communication became a central concern almost immediately. Voyager One's radio signals were already growing weaker as distance increased, spreading out across space as spherical waves. The deep space network on Earth, a global array of massive radio antennas, tracked the spacecraft continuously. Commands were transmitted at the speed of light, but even early in the mission, responses were delayed by minutes. This enforced a new way of thinking. Voyager One had to be trusted to carry out instructions correctly without immediate confirmation. The inner solar system is not empty, even though it often appears that way in illustrations. Voyager One passed through regions filled with solar wind, a constant stream of charged particles flowing outward from the sun. Instruments on board measured this wind continuously, providing data about its speed, density, and variability. These measurements help scientists understand how the sun interacts with space far beyond the planets, shaping a vast bubble known as the heliosphere. even before reaching Jupiter, Voyager One was already contributing to heliophysics, not just planetary science. As the spacecraft moved farther outward, sunlight weakened steadily. Solar panels were never part of Voyager's design, but the diminishing light still mattered. Star trackers relied on clear contrast, and thermal conditions changed as the sun's warmth faded. Voyager 1's nuclear power source provided steady electricity, but even that power had to be rationed carefully. Instruments were cycled on and off, heaters were adjusted, and every watt was treated as precious, even in the early years. Navigation during this phase required extreme precision. Voyager 1's trajectory was refined through small course correction maneuvers, using tiny thrusters. These maneuvers were not about speed, but about direction. A correction measured in fractions of a degree early in the mission could mean the difference between a perfect Jupiter flyby and a miss by millions of kilometers. Navigation relied on Doppler tracking, timing radio signals sent to Voyager 1 and measuring how their frequency shifted when they returned, revealing minute changes in velocity and position. Throughout this long cruise, Voyager 1's speed relative to the Sun remained relatively stable, gradually increasing as it fell outward along its orbital path. Unlike aircraft or cars, spacecraft do not slow down unless acted upon by gravity or thrust. Voyager 1 carried its launch energy with it, conserving momentum in the near vacuum of space. By the time it passed the orbit of Mars and then the asteroid belt, it was already moving faster than any previous human-made object. The asteroid belt itself posed little danger. Contrary to popular imagination, it is not a dense field of rocks, but a vast region where asteroids are separated by enormous distances. Voyager 1 passed through without incident, its instruments quietly recording dust particle impacts and background radiation. Each data point helped refine models of how matter is distributed between the planets. Psychologically, this phase of the mission marked a shift. Voyager 1 was no longer something that could be reached or repaired. Unlike missions in Earth orbit or even lunar space, Voyager was permanently beyond retrieval. Every decision mattered because there would be no second chance. This reality shaped the tone of mission operations: cautious, conservative, and deeply methodical. As months turned into a year, Jupiter grew slowly brighter in Voyager 1's instruments. Long before the first detailed images, scientists could see its increasing influence through subtle changes in particle counts and magnetic field readings. The spacecraft was entering a region where Jupiter's gravity began to compete with the Sun's, preparing the stage for the first major transformation of the mission. By this point, Voyager 1's speed relative to the Sun was already close to what it would carry for the rest of its journey, on the order of 17 kilometers per second. This speed did not feel like motion. It felt like inevitability. Voyager 1 was committed to its path, coasting smoothly through space, accumulating distance every second without effort or resistance. The inner solar system passage was quiet, but it was not idle. It was a period of validation, endurance, and preparation. Voyager 1 proved that it could survive long-term isolation, operate autonomously, and communicate across growing distances. Every successful day increased confidence that the spacecraft could withstand the far more demanding environments ahead. As Voyager One approached Jupiter's realm, the mission transitioned from cruise to encounter. Instruments that had been dormant were awakened. Imaging systems were calibrated. Data storage strategies were finalized. The spacecraft adjusted its orientation to prepare for continuous observation. The long, calm passage through the inner solar system had done its job. Voyager One was ready. By the end of this chapter of its journey, Voyager One was no longer merely traveling away from Earth. It was approaching its first great test, a close encounter with the largest planet in the solar system, where gravity, radiation, and discovery would reshape everything that followed. The quiet phase was ending. The real exploration was about to begin. When Voyager One reached the realm of Jupiter in early 1979, the mission entered a completely new phase. Jupiter is not simply another planet. It is a dominant presence in the solar system, containing more mass than all the other planets combined. Its gravity extends far into space, shaping the paths of asteroids, comets, and spacecraft alike. Long before Voyager One came close enough to capture detailed images, its instruments detected Jupiter's influence through changes in charged particles, magnetic field strength, and radiation intensity. The spacecraft was no longer traveling through ordinary interplanetary space. It was entering the environment of a giant. The approach to Jupiter unfolded slowly. Over several months, the planet grew from a bright point of light into a complex disk. Voyager One's imaging system began capturing photographs that far exceeded anything seen from Earth-based telescopes. Jupiter's cloud bands resolved into intricate structures, swirling storms, turbulent flows, and subtle color variations caused by chemical compounds rising and falling through the atmosphere. One of the most striking features was the Great Red Spot, a massive storm system larger than Earth itself. Voyager One's images revealed that this storm was not static, but dynamic, with complex internal motion and sharply defined edges, reshaping scientific understanding of how long-lived atmospheric systems could exist on gas giants. Voyager One transformed knowledge of Jupiter's atmosphere. Instruments measured wind speeds far higher than previously estimated, revealing powerful jet streams flowing in alternating directions. Temperature profiles showed that Jupiter's atmosphere was structured in layers, influenced by both internal heat and solar radiation. Voyager One demonstrated that Jupiter emits more energy than it receives from the Sun, confirming that internal heat plays a major role in driving its weather. These findings shifted Jupiter from being viewed as a scaled-up version of Earth's atmosphere to a fundamentally different system governed by deep convection and rapid rotation. Jupiter's magnetic field proved even more surprising. Voyager One measured a magnetosphere so vast that it dwarfed the Sun's visible disk when scaled for comparison. This magnetic field trapped enormous quantities of charged particles, creating intense radiation belts that posed a serious risk to the spacecraft. Voyager One passed through these regions carefully, its instruments recording particle energies and field strengths that forced scientists to rethink models of planetary magnetism. The data revealed that Jupiter's magnetic field is generated by motion deep within the planet, likely involving metallic hydrogen under immense pressure. This discovery provided the first real evidence of exotic states of matter existing naturally inside planets. The moons of Jupiter became some of Voyager One's most profound discoveries. Before Voyager, these moons were little more than points of light. Voyager One's close flybys revealed them as worlds in their own right. Io, the innermost large moon, stunned scientists by showing active volcanoes erupting across its surface. This was the first time active volcanism had been observed beyond Earth. Voyager One's images showed plumes rising hundreds of kilometers above Io's surface, driven by tidal heating caused by Jupiter's immense gravity. This discovery proved that geological activity did not require Earth-like conditions and could be powered by gravitational interactions alone. Europa appeared entirely different. Voyager 1 photographed a smooth, icy surface, crisscrossed by dark lines, with very few impact craters. This suggested a young, dynamic surface, constantly reshaped from below. Although Voyager 1 could not directly detect liquid water, its images hinted strongly at a subsurface ocean beneath Europa's icy crust. This idea would later become one of the most compelling targets in the search for extraterrestrial life, all rooted in the first glimpses provided by Voyager. Ganymede and Callisto revealed their own stories. Ganymede showed signs of ancient tectonic activity, with grooves and ridges indicating a complex geological past. Callisto, heavily cratered and ancient, appeared largely unchanged for billions of years, serving as a record of early solar system history. Together, Jupiter's moons demonstrated that planetary systems are not uniform, but composed of diverse worlds shaped by different forces and timelines. Throughout the Jupiter encounter, Voyager 1's trajectory was carefully orchestrated to take advantage of Jupiter's gravity. As the spacecraft passed behind the planet relative to its motion around the Sun, it experienced a gravitational slingshot. This maneuver increased Voyager 1's speed and altered its direction without consuming fuel. Before the encounter, Voyager 1's heliocentric speed was already extremely high, but Jupiter's gravity added several kilometers per second to that velocity, locking in the outward energy that would carry the spacecraft towards Saturn and beyond. This was not a sudden burst of acceleration, but a gradual exchange of momentum spread over hours as Voyager fell into and climbed out of Jupiter's gravitational well. After the Jupiter flyby, Voyager 1's path was permanently changed. Its speed relative to the Sun increased to a level that ensured it would never return inward. From this point on, the spacecraft was effectively committed to leaving the inner solar system forever. Jupiter had acted as a gatekeeper, opening the path outward. The gravity assist did not merely redirect Voyager 1, it finalized its destiny as an interstellar traveler. The images Voyager 1 sent back during this period reshaped humanity's view of the outer solar system. Jupiter was no longer a distant banded sphere. It became a dynamic world, with weather systems, magnetic complexity, and a family of active moons. The sheer volume of data exceeded expectations, forcing scientists to extend analysis timelines and rethink long-standing assumptions. Voyager 1 did not just answer questions. It revealed how many questions had been missing. Communication delays were now significant, stretching to tens of minutes. Commands sent from Earth took time to arrive, and responses took just as long to return. Voyager One operated largely on pre-programmed sequences, executing observations automatically, while Earth listened patiently for results. This growing separation reinforced the sense that Voyager was no longer an extension of human presence, but an independent explorer, acting on instructions written long before. As Voyager One departed Jupiter's vicinity, the planet slowly shrank back into a bright point of light. The radiation environment diminished. Particle counts dropped. The spacecraft entered a quieter region of space once more, carrying with it an expanded understanding of what a giant planet truly is. The data collected during the Jupiter encounter would occupy scientists for decades, informing missions that followed and redefining planetary science itself. Most importantly, Jupiter had changed Voyager One's journey in irreversible ways. Its speed was now greater, its direction fixed toward Saturn, and its role in human exploration firmly established. The spacecraft had proven that gravity could be used as a precise and powerful tool, allowing a small machine to travel farther than any before it, guided not by force, but by timing. As Voyager One continued onward, Jupiter receded behind it, leaving behind not silence, but knowledge. The solar system had revealed itself to be more complex, more active, and more alive than previously imagined. And Voyager One, moving faster now, carried that revelation forward into deeper space. By the time Voyager One approached Saturn in late 1980, the mission had already rewritten humanity's understanding of the outer solar system. Yet Saturn represented something fundamentally different from Jupiter. While Jupiter dominated through sheer mass and raw power, Saturn offered complexity, subtlety, and consequence. The encounter with Saturn would not merely add data, it would force a choice that would permanently shape Voyager One's future. From the moment the spacecraft began to sense Saturn's influence, this encounter carried a weight unlike any before it. Saturn announced itself gradually. Long before Voyager One could resolve the planet visually, its instruments detected changes in the surrounding space environment. Charged particle densities shifted. Magnetic field measurements began to show Saturn's distinct signature. Compared to Jupiter, Saturn's magnetosphere was less intense, but broader and more structured than expected. These early readings hinted that Saturn was not simply a smaller version of Jupiter, but a world governed by its own internal dynamics and balance of forces. As the planet grew larger in Voyager One's cameras, Saturn's rings emerged as one of the most striking features ever recorded in planetary science. From Earth, the rings appeared smooth and continuous. Voyager One revealed them as an intricate system, composed of thousands of individual ringlets, gaps, waves, and braided structures. Subtle gravitational interactions with Saturn's moons sculpted the rings constantly, creating ripples and edges that shifted over time. What had once been imagined as static bands of material were now understood as a dynamic, living system shaped by gravity in real time. Voyager One's images transformed Saturn from an abstract symbol into a physical place. The planet's atmosphere revealed delicate banding, softer and more muted than Jupiter's, yet rich in motion and depth. Wind measurements showed fast-moving jet streams encircling the planet, driven by internal heat rising from Saturn's core. Like Jupiter, Saturn radiated more energy than it received from the Sun, confirming that heat from planetary formation still played a major role in shaping weather patterns. Voyager One showed that Saturn's apparent calm masked a powerful internal engine. Saturn's magnetic field, though weaker than Jupiter's, proved to be remarkably symmetric and well aligned with the planet's rotation axis. This near-perfect alignment puzzled scientists, because planetary magnetic fields typically show noticeable tilt. Voyager 1's data suggested that Saturn's internal structure and rotation created a uniquely stable magnetic environment. This discovery forced revisions to theories of how planetary dynamos operate, particularly in worlds composed primarily of hydrogen and helium. The moons of Saturn provided another layer of revelation. Titan, the largest of Saturn's moons, was the primary target, and the reason Voyager 1's trajectory had been chosen so carefully. Titan was known to possess a thick atmosphere, but its composition and behavior were largely unknown. Voyager 1 flew close enough to probe that atmosphere directly, measuring its density, temperature, and chemical makeup. The data revealed an atmosphere dominated by nitrogen, with complex organic molecules present in trace amounts. This made Titan the only moon in the solar system known to have a dense atmosphere, immediately elevating its scientific importance. Voyager 1 could not see Titan's surface. The thick haze obscured everything below, but this absence of imagery was itself a discovery. It suggested active atmospheric chemistry capable of sustaining complex organic processes over long timescales. Titan became, overnight, one of the most intriguing places in the solar system for understanding prebiotic chemistry. The decision to prioritize Titan meant sacrificing future planetary encounters, but the scientific return justified the cost. Other moons revealed their own surprises. Enceladus appeared small and reflective, its surface bright with ice. Although Voyager 1 could not detect the subsurface ocean known today, its images hinted at geological activity beneath the frozen crust. Mimas displayed a massive impact crater that nearly shattered the moon, offering insight into the limits of structural stability for small bodies. Each moon told a different story, adding depth and diversity to Saturn's system. Throughout the Saturn encounter, Voyager 1's path was shaped with extraordinary precision. The spacecraft passed behind the planet relative to its motion around the Sun, using Saturn's gravity to reshape its trajectory. This gravitational assist did not add as much speed as Jupiter's, but it refined Voyager 1's direction and locked in its escape path from the planetary region. After Saturn, Voyager 1's heliocentric speed stabilized at approximately 17 kilometers per second, a velocity sufficient to carry it beyond the influence of the Sun over time. Unlike Jupiter, Saturn represented a point of no return. The closed Titan flyby required Voyager 1 to pass in such a way that its trajectory was bent sharply out of the plane of the solar system. This ensured that it would not encounter Uranus or Neptune. From this moment onward, Voyager 1's mission shifted from planetary exploration to interstellar journey. The spacecraft was no longer traveling from planet to planet. It was traveling away. The images sent back during this phase were among the most iconic of the entire mission. Saturn's rings, seen edge-on and backlit by the Sun, revealed their thinness and complexity. Shadows cast by the rings onto the planet's atmosphere illustrated their three-dimensional structure. These images were not merely beautiful. They carried quantitative information about particle size, ring thickness, and gravitational interactions that could not be obtained any other way. Communication delays were now significant, approaching an hour for a round-trip signal. Voyager One operated almost entirely autonomously during the encounter, executing preloaded observation sequences while Earth waited for confirmation. The spacecraft's onboard systems managed power, orientation, and data storage with minimal intervention. This autonomy was not a luxury, it was a necessity. The growing distance ensured that Voyager One was becoming increasingly independent with every passing day. As Voyager One departed Saturn, the planet slowly diminished in the rear-facing cameras. Instruments recorded the gradual fading of Saturn's magnetic influence and the return to the quieter environment of interplanetary space. But something fundamental had changed. The spacecraft's future was now fixed. Its speed, direction, and destiny were no longer adjustable through planetary encounters. Saturn marked the moment when Voyager One ceased to be a visitor and became a voyager in the truest sense of the word. It had completed its primary mission, exceeded expectations, and entered a phase no one had originally planned in detail. The solar system lay behind it, and interstellar space lay ahead. The Saturn encounter was not the end of exploration, but the end of choice. Voyager One had been aimed outward deliberately, and gravity had done the rest. What followed would unfold slowly, quietly, and over distances measured not in astronomical units, but eventually in light itself. As Voyager One moved onward, its instruments continued to listen, measure, and record, carrying forward the legacy of Saturn's rings, Titan's atmosphere, and a decision made years earlier on Earth. The spacecraft did not accelerate further. It did not change course. It simply continued, steady and unhurried, into deeper darkness. The planetary era of Voyager One was complete. The interstellar journey had begun. After the Saturn encounter, Voyager One entered a phase of the mission that was unlike anything that had come before it. The spacecraft was no longer navigating between planets, nor preparing for another close flyby. Instead, it began a gradual, irreversible transition out of the planetary region of the solar system altogether. This transition did not occur at a single boundary or moment. There was no line to cross, no sudden change in environment. Leaving the planetary system is a process, measured in years and astronomical units, defined by diminishing gravitational influence rather than physical separation. In practical terms, Voyager One was now moving on a trajectory that would never again bring it close to a major planet. The sun remained the dominant gravitational force, but its hold was weakening slowly with distance. The combined influence of the giant planets, which had once shaped Voyager's path through gravity assists, faded into the background. Voyager One's heliocentric speed stabilized at roughly 17 kilometers per second, a velocity that would remain nearly constant for the rest of its operational life. Without engines firing and without further planetary encounters, The spacecraft coasted onward, conserving the energy imparted to it by gravity years earlier. During this period, the mission formally transitioned from planetary exploration to what NASA called the interstellar mission. This change was not marked by fanfare. It was an administrative and conceptual shift, reflecting a new scientific focus. Voyager One's instruments were repurposed to study the environment between the planets rather than the planets themselves. Measurements of charged particles, magnetic fields, cosmic rays, and plasma became the primary data stream. The spacecraft was now a probe of space itself, not of worlds embedded within it. The region Voyager One traveled through during these years is often imagined as empty, but in reality, it is structured and dynamic. The solar wind, a continuous flow of charged particles emitted by the sun, fills the solar system, carrying with it the sun's magnetic field. This outflow creates a vast bubble around the sun known as the heliosphere. Inside this bubble, conditions are shaped by solar activity, solar flares, coronal mass ejections, and the 11-year solar cycle all influence particle density and magnetic structure. Voyager One moved steadily outward through this environment, recording how it changed with distance. As Voyager One passed beyond the orbit of the outermost planets, its instruments detected gradual shifts in the solar wind. Particle densities decreased. The magnetic field weakened and became more irregular. These changes were subtle and unfolded over years, not days. The spacecraft crossed no clear boundary, marking the end of planetary space. Instead, it revealed that the solar system fades into interstellar space through a long, complex transition zone, rather than a sharp edge. Communication during this phase became increasingly challenging. Voyager One was now so distant that radio signals took many hours to travel between Earth and the spacecraft. Commands had to be planned carefully, often weeks in advance, and transmitted as long sequences. The spacecraft executed these instructions autonomously, storing data on board until it could be transmitted back to Earth at very low data rates. Each bit of information required patience. Listening became as important as transmitting. Power management grew more critical with every passing year. Voyager One's nuclear power source produced steadily less electricity as its radioactive fuel decayed. Engineers began making difficult decisions about which instruments to keep active and which to turn off permanently. These choices were guided by scientific priority and by the need to preserve core systems such as communication and orientation control. Voyager One was slowly shedding capabilities, but it was doing so deliberately, extending its life as long as possible. During this long outward journey, Voyager One provided humanity with the first continuous measurements of the distant heliosphere. It showed that the solar wind does not simply weaken smoothly with distance. Instead, it fluctuates, compresses, and interacts with incoming material from interstellar space. These interactions create regions of turbulence and complexity, reshaping previous assumptions about how the sun's influence ends. The sense of distance during this phase is difficult to convey intuitively. Voyager One moved farther from Earth every second, yet its speed felt unchanged. Distance accumulated invisibly. Earth became just another bright point of light behind it, indistinguishable from the stars. The sun's apparent brightness diminished, though it remained the strongest nearby source of light and gravity. Voyager One existed in a state of isolation that no human-made object had ever experienced before. Conceptually, this phase marked a shift in how humanity related to the spacecraft. Voyager One was no longer an active explorer visiting destinations. It was a long-term observer, embedded in a slow flow outward. Its mission timeline stretched beyond individual careers, beyond generations of scientists and engineers. People who had worked on its launch retired. New scientists learned to interpret its data. The spacecraft itself remained unchanged, following instructions written years earlier. Leaving the planetary system also meant leaving behind the gravitational complexity of the inner solar system. Planetary resonances, orbital perturbations, and close encounters were gone. Voyager One's path became simpler, governed primarily by inertia and the weak pull of the distant sun. This simplicity brought stability. The spacecraft's motion could be predicted far into the future with high confidence. Nothing lay ahead that would significantly alter its course. Yet simplicity did not mean uniformity. The space Voyager One traveled through was shaped by forces far larger than planets. Galactic cosmic rays, high-energy particles originating outside the solar system, became increasingly prominent as the shielding effect of the solar wind weakened. Voyager One measured these particles directly, providing insight into radiation environments that shape the galaxy itself. These measurements had implications not only for astrophysics, but for future human exploration beyond the solar system. As years turned into decades, Voyager One crossed distances that once seemed unimaginable. Astronomical units accumulated quietly. Communication delays stretched longer. The spacecraft continued to operate, its systems aging gracefully, its instruments still returning data. There was no sense of arrival, only of continuation. Leaving the planetary system was not an event. It was a condition. By the end of this phase, Voyager One was no longer meaningfully part of the solar system as a collection of planets. It was part of a larger structure, the heliosphere, and approaching its outer boundary. The planets lay far behind. Ahead lay the region where the sun's influence would finally give way to the interstellar medium. Voyager One did not accelerate further. It did not change direction. It simply continued outward, steady and patient, carrying with it everything it had learned about planets, space, and the gradual fading of the sun's reach. The journey between stars was no longer theoretical. It had begun. As Voyager One continued outward beyond the planetary region, the most significant change it encountered was not a visible one. There were no landmarks, no dramatic transitions, no sudden darkness. Instead, the transformation unfolded invisibly, through changes in particles, fields, and pressures that could only be detected by sensitive instruments. Voyager One was approaching the outer boundary of the sun's influence, a vast and complex region where the solar wind slows, bends, and ultimately yields to the environment between the stars. This boundary is not a single wall, but a layered transition shaped by motion, magnetism, and time. The sun constantly emits a stream of charged particles known as the solar wind. This flow travels outward in all directions, carrying with it the sun's magnetic field, and shaping a giant bubble in space called the heliosphere. Inside this bubble, conditions are dominated by solar activity. Outside, it lies the interstellar medium, a sparse mixture of gas, dust, and magnetic fields that fills the space between stars. Voyager One's task during this phase of the mission was to measure how these two environments meet and interact, something that had never been observed directly before. The first major transition Voyager One encountered was the termination shock. This is the region where the solar wind, traveling faster than the speed of sound in the surrounding plasma, abruptly slows down due to pressure from the interstellar medium. Voyager One crossed this boundary in late 2004. Instruments recorded a sharp drop in solar wind speed, accompanied by changes in particle energy and magnetic field behavior. This crossing confirmed long-standing theoretical predictions, but also revealed that the termination shock was far more irregular and dynamic than expected. Beyond the termination shock lies the heliosheath, a turbulent region where slowed solar wind piles up and flows sideways, distorted by external pressure. Voyager One spent many years traversing this region. Conditions here were unstable and constantly changing. Particle densities fluctuated, magnetic fields twisted and folded. Cosmic rays from outside the solar system became increasingly prominent as the sun's shielding weakened. This was not empty space, but a region of interaction and compression where two vast systems negotiated their boundary. One of the most important discoveries Voyager One made in the heliosheath was the gradual increase in galactic cosmic rays. These high-energy particles originate from distant supernova and other energetic events in the galaxy. Inside the heliosphere, the solar wind deflects many of them. As Voyager One moved farther outward, this protection diminished. Instruments recorded a steady rise in cosmic ray intensity, indicating that the spacecraft was approaching the point where interstellar space would dominate. At the same time, measurements of the sun's magnetic field began to change. Voyager One observed that the solar magnetic field weakened and became less orderly with distance. Instead of a smooth, spiral structure carried outward by the rotating sun, the field lines appeared compressed and tangled. This behavior suggested that the heliosphere was being squeezed and shaped by the surrounding interstellar magnetic field, rather than expanding symmetrically as once imagined. In August 2012, Voyager One crossed the heliopause, the boundary where the pressure of the solar wind is balanced by the pressure of the interstellar medium. This moment is often described as Voyager One leaving the solar system, but technically, it marked the spacecraft's entry into interstellar space, while still gravitationally bound to the sun. Instruments detected a sudden and sustained drop in solar particles, accompanied by a sharp increase in interstellar cosmic rays. Plasma density measurements confirmed that Voyager One was now immersed in material originating beyond the sun's influence. Importantly, this crossing did not involve a dramatic change in direction or speed. Voyager One continued moving outward at approximately 17 kilometers per second, a velocity established years earlier by planetary gravity assists. What changed was the environment. The spacecraft was no longer surrounded by material shaped primarily by the sun. It was now sampling the local interstellar medium directly, becoming humanity's first emissary to the space between stars. The magnetic field beyond the heliopause revealed another surprise. Instead of rotating abruptly, the magnetic field direction remained closely aligned with the solar field, suggesting a more complex interaction between solar and interstellar magnetism than expected. This challenged existing models and demonstrated that the boundary between stellar systems is not a clean separation, but a region of continuity and coupling. Voyager One's measurements forced scientists to revise their understanding of how stars interact with their galactic environment. Throughout this transition, communication with Earth continued, though at ever-increasing delays. Signals took more than 17 hours to travel one way. Voyager One operated almost entirely autonomously, executing commands sent long before and returning data slowly, bit by bit. Every measurement mattered. There would be no second chance to observe this region directly. Power constraints became increasingly important during this phase. With each passing year, Voyager One's energy supply declined. Engineers made careful decisions about which instruments to keep active, prioritizing those capable of measuring particles, magnetic fields, and plasma. These choices ensured that Voyager One could continue contributing valuable data even as its capabilities narrowed. Exiting the solar magnetic field did not mean entering silence. Interstellar space is not empty or inactive. It contains structure, motion, and energy, shaped by the collective influence of countless stars. Voyager One's continued measurements provide a local perspective on this environment, offering insight into conditions that shape star formation, cosmic radiation, and the broader dynamics of the galaxy. By the end of this phase, Voyager One had completed a transition that began decades earlier at launch. It had moved from Earth's vicinity to planetary space, from planetary space to the heliosphere, and from the heliosphere into interstellar space. Each step was gradual, defined by physics rather than ceremony. The spacecraft did not announce its departure. It simply continued onward, measuring as it went. The sun was now one star among many behind it, its magnetic influence no longer dominant. Ahead lay open interstellar space, vast and largely unexplored. Voyager One carried with it a record of this crossing, encoded in radio signals slowly returning to Earth, allowing humanity to understand, for the first time, how a star's influence fades into the galaxy beyond. The journey outward did not end here. It entered a new context, where distance would soon be measured not in astronomical units, but in light itself, and where time would stretch even more gently as Voyager One continued its quiet passage between the stars. By the time Voyager One entered interstellar space, the mission had already extended far beyond its original design lifetime. What remained was no longer a sequence of encounters, but a steady accumulation of distance and time. Voyager One continued moving outward at roughly 17 kilometers per second, a speed that feels abstract until translated into light itself. At this distance, communication with Earth is no longer measured in minutes, but in many hours, and every exchange becomes a reminder that Voyager One now exists on a scale where human intuition struggles to follow. Voyager, one's distance from Earth can be understood most clearly through light travel time. radio signals move at the speed of light, so when Earth sends a command, it travels outward for more than 20 hours before reaching the spacecraft. A response takes just as long to return. This means that any interaction with Voyager One is separated by nearly 2 full days of waiting. There is no conversation, only correspondence. The spacecraft is currently more than 20 light hours away from Earth, and that distance grows continuously. Each day, Voyager One adds several light minutes to its separation, carrying it farther into interstellar space. To place this in perspective, light takes about 8 minutes to travel from the Sun to Earth. Voyager One is now many times farther away than that, well beyond the region where sunlight meaningfully illuminates space. The Sun, from Voyager One's vantage point, is no longer a bright disk, but an intense star among others. Even so, Voyager One remains gravitationally bound to the Sun, following a long, slow arc around the center of the galaxy that will take hundreds of millions of years to complete. Looking further ahead, Voyager One will eventually reach distances measured in light days rather than light hours. A light day is the distance light travels in 24 hours, and Voyager One is slowly approaching that scale. Reaching 1 full light day from Earth will still take many years. Beyond that lies the milestone of 1 light year, a distance so large that it is rarely associated with spacecraft at all. At its current speed, Voyager One will require roughly 17,000 years to travel 1 light year. This number alone illustrates the vastness of interstellar space and the patience required to cross it. Voyager One's power supply defines the remaining active years of the mission. The spacecraft is powered by radioisotope generators that convert heat from decaying plutonium into electricity. This process is reliable and steady, but it is not infinite. Each year, the available power decreases slightly as the radioactive material decays. Engineers on Earth manage this decline carefully, turning off non-essential systems one by one to preserve core functionality. Cameras were powered down decades ago. Other instruments have followed, not because they failed, but because energy had to be conserved. Today, only a small set of instruments remains active, focused on measuring magnetic fields, charged particles, and plasma density. These instruments continue to return valuable data about the interstellar environment, providing humanity's only direct measurements from beyond the Sun's magnetic influence. Even this capability will not last forever. Sometime in the early 2030s, Voyager One is expected to lose the ability to power its remaining scientific instruments. After that, communication itself will eventually cease as power drops below the threshold needed to operate the transmitter. When that moment arrives, Voyager One will not stop moving. It will simply stop speaking. The spacecraft will continue on its trajectory silently, carrying its structure, its instruments, and the golden record onward through interstellar space. There will be no final signal, no announcement, no confirmation of silence. The mission will end quietly, not with failure, but with completion. Despite this, Voyager One's journey is far from over in a physical sense. Long after its last transmission, it will continue traveling through the galaxy. In roughly 40,000 years, Voyager One will pass within a few light years of another star system. It will not stop. It will not slow significantly. It will simply pass through another region of the galaxy, unnoticed, unchanged, carrying with it the evidence that it was once built by a technological civilization orbiting a small star far behind it. Over much longer timescales, Voyager One will orbit the center of the Milky Way again and again, its path altered only by weak gravitational interactions with stars and interstellar clouds. The spacecraft may persist for millions of years. It may eventually collide with dust, gas, or even a star, though the probability is extremely low. More likely, it will continue drifting indefinitely, becoming an inert artifact embedded in the slow motion of the galaxy. What makes Voyager One remarkable at this stage is not what it will do, but what it has already done. It has extended human presence beyond the planetary region. It has provided the first direct measurements of interstellar space. It has demonstrated that a machine built for a few years of exploration can remain functional for decades through careful design and restraint. Voyager One is not an active explorer in the traditional sense anymore. It is a long-term witness. Distance, power, and time now define the mission. Distance grows silently. Power fades predictably. Time stretches beyond any planning horizon. Yet even as these constraints tighten, the mission remains complete. Voyager One continues to return data today, quietly expanding humanity's understanding of the space between stars, even as it approaches the limits of its ability to communicate. There is something uniquely fitting about this phase of the mission. Voyager One does not rush toward an end. It does not attempt to achieve one last dramatic discovery. It simply continues, measuring what it can, as long as it can, without urgency. The spacecraft exists in a state of gradual transition, moving from an active scientific instrument to a silent traveler, carrying its legacy forward without intervention. As Voyager One moves farther away, Earth becomes just another point of light behind it. And eventually, even that point will fade beyond the reach of its antenna. Yet the path Voyager One follows remains clear, defined by physics rather than intention. It will keep moving outward, steadily and patiently, long after its human story has concluded. The mission's final years are not about achievement or closure. They are about endurance, about allowing a journey to complete itself naturally. Voyager One continues into the dark, not because it must, but because nothing remains to stop it. Once Voyager One's instruments eventually fall silent, the spacecraft will not stop moving. Its journey will simply change character, shifting from an active mission into a purely physical trajectory governed by gravity and inertia alone. Voyager One is currently traveling through interstellar space at a speed of roughly 17 kilometers per second relative to the Sun, and that speed will remain almost unchanged for millions of years. There is no mechanism left to accelerate it, slow it significantly, or alter its course in any meaningful way. The path ahead is already written in the language of celestial mechanics. In the near future, measured in decades rather than centuries, Voyager One will continue to increase its distance from Earth by several light minutes each year. Communication delays will grow from more than 20 hours, one way to even longer spans, until eventually power constraints prevent any further contact at all. When that moment arrives, Voyager One will be farther from Earth than any functioning human-made object has ever been, existing beyond real-time awareness, its position known only through extrapolation and memory. Yet even then, its motion will be predictable, because space at this scale is remarkably stable. As years turn into centuries, Voyager One will move farther into the local interstellar medium, passing through regions of gas and dust so sparse that collisions with individual atoms are rare. Even at 17 kilometers per second, it would take tens of thousands of years for Voyager One to encounter anything dense enough to noticeably affect its trajectory. Interstellar space is not empty, but it is forgivingly vast. The spacecraft will drift quietly, unperturbed by most of what lies around it. In approximately 17,000 years, Voyager One will reach a distance of 1 light-year from the Sun. This milestone carries symbolic weight, but physically, it will mean very little. There will be no marker, no change in environment, no shift in direction. A light-year is simply a human unit, defined by how far light travels in a year, not by any physical boundary. Voyager One will cross that distance without noticing, just as it crossed every astronomical unit before it. Farther ahead, on timescales of tens of thousands of years, Voyager One will pass relatively near other stars. One such encounter is expected in roughly 40,000 years, when the spacecraft will pass within a few light years of another star system. Even then, near is a relative term. The distance will still be vast, far too great for any meaningful interaction. Voyager One will not be captured by another star. It will not slow. It will simply pass through another region of the galaxy, unchanged. Over hundreds of millions of years, Voyager One will complete an orbit around the center of the Milky Way, along with the Sun and billions of other stars. Its path will slowly curve, shaped by the galaxy's gravitational field. This motion will be smooth and gradual, almost imperceptible on any human timescale. The spacecraft will become part of the galaxy's general circulation, one more small object, moving quietly among countless others. The probability that Voyager One will ever collide with a planet, a star, or even a large piece of interstellar debris is extremely low. Space is simply too vast. Much more likely is that Voyager One will persist for millions of years as an inert object, slowly accumulating microscopic damage from cosmic radiation and dust impacts, yet remaining largely intact. The golden record mounted to its side may endure far longer than any human structure on Earth. Eventually, over timescales difficult to truly imagine, even the materials of Voyager One will degrade. Atomic bonds will be disrupted. Surfaces will erode. The spacecraft will lose its recognizable shape. But even this process will take enormous amounts of time. Voyager One will not vanish. It will transform gradually, becoming indistinguishable from other debris moving through interstellar space. What makes Voyager One's future remarkable is not that it will arrive somewhere, but that it will never truly arrive at all. Its journey has no destination. It is not aimed at a particular star or system. It is aimed outward, into the general structure of the galaxy. This open-endedness is not a flaw. It is the essence of the mission. From a human perspective, Voyager One represents an extension of presence rather than control. It is not a probe that reports back indefinitely, nor a vehicle meant to return. It is a trajectory, a motion set in place once and allowed to continue. In that sense, Voyager One is closer to a message than a machine. Not because of what it carries, but because of where it goes. Long after the details of its mission fade from memory, Voyager One will still be moving. Long after the deep space network falls silent, the spacecraft will still exist. It will carry with it the fact that a technological civilization once emerged around a small star and sent a machine outward, not to conquer or claim, but simply to explore and to continue moving. The future of Voyager One is quiet by design. It does not involve dramatic encounters or final moments. It involves distance accumulating slowly, light taken longer to travel, and time stretching beyond usefulness as a unit of measurement. Voyager One will continue along its path, steady and unhurried, long after its voice is gone. In the end, Voyager One's trajectory is not about where it will be, but about the decision that set it in motion. Once launched, the journey became inevitable, and once begun, it became something that could only be allowed to finish on its own terms.
you.